The sooner we start, the sooner we end. The sooner reception will start.
I'm sorry, that was my...
Take your seat, please, or take someone else's chair also.
Okay, can you hear me? Yes. Okay, so welcome to the afternoon session, the last session of the first day. The session title is different from what you can read in your program, where things are neither provocative nor surprising, structure, formation, and dark matter. The actual subject of the discussion session and the morning session that we prepared pose this question. Is a theory beyond cold dark matter, or the lambda cold dark matter, needed to describe structure formation?
The answer is no.
Something happened though after.
That's the end of the class.
Okay.
my whole thing was my slides disappeared. Yeah. But so this is the this big subject, and actually people organize conferences on this subject. There was a conference in 2015. I'm sure in this audience there's quite a few people who were there. I was, and there is the summary of the conference, which has 100 pages on archive that you can read. So to do this in one panel is quite a challenge on itself. And so we'll probably limit ourselves to actually discussing only part of this problem, but you'll hear perspective from 3 distinguished panel members, and we'll have some discussion to sort of get a snapshot of this subject of the current 2019. So some things have changed in the last 4 years, and we'll try to get a snapshot of this. So I think I'll start with something non-controversial, which is CDM is a highly successful and well-tested model of structure formation, and this is probably not something that somebody will contest with. On large scales, the model is remarkably successful. It was introduced close to 40 years ago as one of the possible models of structure formation, and it withstood 40 years of comparisons with data, and in fact it became the paradigm, the model of structure formation. And the question is, why are we unhappy with it? So today, this morning, there is some discussion about why the CDM is boring and why is it boring. To me, when I was thinking about this this question, it reminded me of this famous song. I don't know how many people know the song by Peggy Lee. Is it All There Is? Where the song can be about anything. This is an example when she's talking about how she was a little girl and the house caught fire and she was seeing her world coming down in flames. And then in the end, she thought, is there all there is to the fire? You know? So after we saw 40 years of successes for the CDM, the question to pose, of course, is that all there is to CDM, to documentary structure formation. To some extent, you know, this is by itself is a testament how successful the model is if we're bored with it. It became so standard that it's boring. But of course, one of the reasons that it's driving this field is, and it's driving these questions, is the fact that on small scales where the structure formation theory is not completely finished yet, it's not clear that CDM passes all of the observational tests, and there are challenges and tensions that people are discussing on small scale specifically. We were asked by organizers to be provocative and surprising, and this morning already there was some of the results of the parallel session on this subject, which were both provocative and surprising. And this is a scorecard from one of the reports by Alison Brooks that checked all the challenges for 3 models for CDM, warm dark matter, and self-interacting dark matter. And as you can see, they all pass the observational tests. But the caveat is that they all pass observational tests only when you add baryons. So with this scorecard, we can look much more mixed if there are no baryons, but once you start thinking about baryonic effects, then all models are fine. And what will be surprising, maybe it will be surprising after this panel, after you hear everything that our panelists have to say, is that maybe these models, self-interacting dark matter, may be the favorite one. We'll see if everybody on the panel and everybody in the audience agrees, but that's part of the surprise.
What is diversity?
Just wait. You'll be educated.
We heard from Rocky something.
So without further ado, I'll introduce the panel. So the panel is Wolf J, who will go first. The Wolf is a well-known cosmologist who actually did work on structure formation and is responsible for many of the tests that CDM withstood over the last couple of decades. But he's also somebody who thought about alternatives to CDM, modifications to gravity, and so on. So Wolf will talk about a variety of things that his perspective on this subject, and particularly looking at large scales and sort of cosmological scales. Risa Wexler will go first. She'll talk about CDM and the CDM performance on small scales. And then Manoj Kapligat will try to advocate for some alternatives. In particular, will try to convince us, or at least will try to be provocative and surprising. Will try to convince us that, that alternatives to CDM is needed when it comes to structure formation. So let's welcome the first panel speaker, Wolf J.
Thank you, Andrey. Let's see if my laptop talks too. Great. Can everyone hear me okay in the back? Thank you. So our charge was to consider the question, excuse me. I'm trying to figure out. Okay. Is a theory beyond CDM needed to describe structure formation? We had a very fun session this morning. I'm not going to try to summarize what all these wonderful speakers said, but some of the key words are in blue. Fuzzy dark matter and self-interacting dark matter seem to be popular research topics. Simulations of just the gravitational piece and the baryonic piece both are clearly critical, and we heard some great talks on those. And observations of strong lensing, satellite galaxies, tests of the core cusp problem or alleged problem. And Annika Peter told us never to use too big to fail, that phrase, and then proceeded to use it a dozen times herself. So I thought I should mention that. It's a fake problem. Sorry?
Missing satellite.
Missing satellite. Yes. So to the extent that everything in cosmology is connected, I'm going to begin where our previous panel left off, that we seem to be in or on the brink of a crisis in cosmology, at least of the standard model, in that the universe today is expanding faster and probably has smaller fluctuations than you'd expect from CMB observations translated in time using general relativity and lambda CDM. So you can pick whichever color you hate the most and try to change that. One question we'll consider is whether there's other evidence for the breakdown of this model, in particular the small scales that were discussed in the document session. So I don't need to remind you that this is by some measures of community consensus, the most significant tension in cosmology, H0. And what new physics could resolve the tensions to the extent that it impacts dark matter, I thought it useful to summarize it. Unusual dark energy properties, new species or interactions, modified gravity. There's an emerging consensus that new physics before recombination is the likely answer, because data at late times strongly constrains omega matter and other parameters. So if you try to tweak the late time ingredients of the universe, you run into trouble very quickly.
Was that the conclusion from the previous panel? No. Not at all, right? Why do you say that there is an emerging consensus?
I have 15 more minutes to express my opinions. Then we can
it's
discuss
opinion.
things. There's also a question mark there. So that's how most theorists seem to be speaking with their feet. They're developing these models of early dark energy and other interactions in the pre-recombination universe. Of course, I myself have worked on the other end, as you heard from Harry Desmond. There, one can certainly come up with models that tweak physics in the the local universe. It's useful to remind ourselves of this color scheme that at the time of recombination, the lower panel shows that the constituents of the universe were dramatically different from the present universe. So dark matter was much more important. Photons and neutrinos had a pretty good showing, which is what tells you that if you introduce new physics in any of those sectors, you can change the story of H0. And in particular, you need to tweak only a fraction of dark matter to have it decay or something to change the story of H0. Of course, CMB data themselves constrain what you can do with interactions and decay. So let's jump to large-scale structure. So I'm going to take you through a few decades in length scale of the late universe's large-scale structure. And then Risa and Manoj are going to take you another few decades into the cores and into the inner profiles of halos. So this is a dark matter map from the Dark Energy Survey, whose analysis is ongoing. So we expect to have another factor of 4 improvement in area and measurement accuracy. And our friends in the KIDS Subaru HSC surveys are also analyzing galaxy and lensing data, and DESI is beginning commissioning any day now, is that right? So in redshift space distortions, also we have ongoing advances. So these are the lensing shear correlations in many redshift bins from DES. I don't want to dwell on these. But I'll jump to this plot from the Planck paper. That is lambda CDM the right model if you translate all of these observations, the CMB as well as low redshift observations of galaxy clustering, Lyman alpha, and lensing, they sure seem to fall on a single plot of the 3D power spectrum today. So this is the 10% level evidence that we have found the standard model of cosmology. But let's look more closely. We heard from Simon this morning that there is a second tension in the amplitude of mass fluctuations. So on the left is the dark energy survey constraints and sigma 8 and omega matter. On the right is a redshift space measurement from BOSS and lensing from KIDS. And this panel shows you one way to see the tension in S8 and omega matter. You see that Planck versus this combination are in 2 sigma tension. So there's a number of data sets, and no one data set is showing any convincing tension at more than 2 sigma, but there's quite a few different observables and different surveys that show it. So this is an old plot, but I like Wayne's color scheme, so I'm using it. It summarizes the H0 tension and the sigma 8 tension. It's worth noting that the central values of sigma 8 since 2013 have shifted by more than a sigma, but it's still at about the 2 sigma level. So should we impeach? Of course, I'm talking about the standard model of cosmology. Proceedings have begun in the sense that the GR plus the lambda CDM model is being supplemented with additional ingredients. But do these ingredients point to new dark matter physics? Another attempt at describing a community view is that the range is not necessarily to not at all. I'm not hearing a lot of, yes, it's very likely dark matter physics, or here's a compelling model that a lot of people are finding interesting. So that's my view. Manoj will hopefully provide an interesting counter view. Suppose you take CDM to be entirely successful, what is left in dark matter studies? Well, there is the very interesting question of what the CDM is. So I find the possible microphysics of CDM likely very interesting. And there's a second possibility that simplicity is not a compelling guide. So it's very interesting to consider the possibility that there's something like CDM and another fraction of a different particle or a primordial black hole or some other interaction that's in the dark sector or dark sector coupled to the standard model. This would be a major discovery, and we know that new tools are becoming available to pursue these. So my political consultant, Mark Hamiankowski, has come up with this elaborate mapping of dark matter particles to Democrat candidates. I believe he showed this at a meeting a couple of months ago, and we'll be speaking on a different topic tomorrow, so give me the liberty of showing the slide. So you can pick your favorite dark matter candidate or Democrat candidate and see whether you like the mapping or not. It's interesting that fuzzy dark matter is associated with somebody I don't actually recognize. Sorry, man. And that Joe Biden got probably the least favorite acronym you would want on this. So could any of them win? In principle, the 538 website comes up with a story every time somebody announces their candidacy. They are so-and-so's path to the White House. So let's move to present-day observations and talk about what are the stress tests of CDM and what kind of tensions we are seeing. Let's look at galaxy clusters. This is a picture of a simulated cluster from Beamer and Kravtsov simulations. And it looks nicer on my laptop, of course, but you can see that it's very messy, violent, and isotropic. And yet, with various observations, in this case strong lensing, you can measure to the 10% level the profiles, the full matter profiles of these clusters individually. These are the various multiple images at a range of radii. So with strong lensing, you get to 1/10 of the virial radius. With weak lensing, shown here, you can go to the virial radius and well beyond. And you can use the galaxy profile. So these are the projected profiles of a few thousand clusters in the dark energy survey. And you can see the measurements are at the 10% level per bin, even in lensing, and at a few percent overall. So we have quite a dynamic range to test the dark matter profiles around galaxy clusters and compare them to the profiles of galaxies. And this entire range shown is dark matter dominated. What does it take to do such an analysis? You need a model that you can use to compare simulations to data, and I'm not going to tell you what all these terms are, but there's nearly 10 parameters. On 2 or 3 of them you have reasonable priors, but it's still 6 or 7 pre-parameters. So with these kind of tests, we have measurements that are at this level, spanning 3 decades in length scale. And yet, the alternatives to CDM that are discussed today, they fit all this data. And that's pretty much by design, because CDM has been so successful that models like fuzzy dark matter are designed to be indistinguishable from CDM by the time you get to 1/10 of a megaparsec. So that's an interesting thing to note, but it is still an important exercise to take these beautiful measurements, which are going down by a factor of 2 in our current analysis, and stress test CDM through better predictions. Because right now we are theory limited in being able to test measurements over this entire range of scales, not measurement limited. So we need models for this quasi-linear scales that we think we have, the 1 to 2 halo transition that has been surprisingly difficult, and well inside halos, but still in the dark matter dominated regime. So this is ongoing work that may yet show a breakdown of CDM. There's new things you can measure. One of my favorites, I'll spend a couple of minutes on, is cluster splashback. An idea introduced by Andrey and colleagues from simulations, and now seen in data. So this is profiles of galaxy clusters detected with SZ and optical, and there is evidence, we believe, of a boundary that indicates the point at which particles and galaxies turn around. That's called splashback. And the initial results showed that it was the measured boundary, shown here as the minimum of the log derivative of the profile, is smaller than expected from simulations. We have since learned that that may well be an artifact of optical cluster finding. So this is an exercise we are now doing with a much bigger sample of SC-selected clusters. So these are some of the people in the room who've worked on this analysis. We've shown that this can be used as a test of both gravity and self-interacting dark matter. So in a paper led by Sushmita Adhikari, we showed that if you look especially at dynamical friction and how it impacts galaxies of different sizes falling through clusters, you get 20% shifts in the location of this radius, which we are already measuring to the 5% level. So this is a useful test. And in another paper, Orko Banerjee and collaborators showed that self-interacting dark matter alters both the inner profiles, these are the error bars expected from DES and LSST, and the signatures of different SIDM parameters, as well as splashback, which I haven't shown. So these are some of the ongoing tests. No evidence of a serious breakdown yet. There's another kind of test I wanted to describe, which is, you might call them equivalence principle tests, which is the test of, does dark matter fall under gravity the same as stars and gas and black holes? And we have motivation from both modified gravity theories and, of course, dark matter interactions that this could break. You know, obviously, if dark matter is interacting with itself as it falls, then it's going to fall slower than, say, stars, which are truly collisionless for all practical purposes. So, in addition, if dark matter interacts with baryons, you would see effects. Some of us have worked on modified gravity theories, scalar tensor type theories that have a screening mechanism to recover GR in the Milky Way of the solar system, but outside of us, in other galaxies, they would affect stars and, say, H1 and dark matter differently. So there's a number of signatures that you can look for, and the bullet cluster-like systems are one example in which, you know, it's now been over a decade that we've seen that there appears to be no evidence for dark matter and stars moving differently. Whereas if dark matter had self-interactions, they would. So this gives us a useful constraint, and an open question is, can such studies, because now we can assemble much larger samples of merging clusters, can they get us another factor of 10 improvement in the interaction cross-section? And that's a complicated story. One can have fun with other systems, disk galaxies and dwarf galaxies. So this plot shows you know, the kind of warp in disk galaxies that the Milky Way and other galaxies have. And this plot, this is a paper led by Lucas Secco, a student at Penn, and Amanda Farah, now a graduate student at Chicago, shows that if you have self-interactions, then the disk and the dark matter get displaced from each other, and you get a warping of disk. So we stared at a number of images like this, and you can get some surprisingly beautiful straight disk galaxies and galaxy clusters. So we don't have a paper yet, but CDM seems to survive this test as well. A while ago, Kesden and Kamyankowski used the leading and trailing tidal tails of the Sagittarius dwarf galaxy to do a similar equivalence principle test of dark matter interacting with baryons. So all of these tests are very rich because we have beautiful data coming in. And the last test I wanted to show is a field I don't know much about, but there's this very intriguing paper by Anna Bhavana and collaborators who have, you know, a series of papers on this topic, looking at Gaia data and looking at these, you know, enormous on the sky and very delicate stellar streams formed by, you know, ripping of globular clusters, and the fact that this one shows 2 gaps and 1 spur, and with simulations you can reconstruct the dynamical history, and there's very little freedom, these authors demonstrate, in being able to produce these features unless it had an encounter with, you know, 10 to the 8-ish subhalo. And this is just 1 stream and 1 encounter, but it mildly disfavors CDM. So this is, of course, a subject of debate, and it would be wonderful to have more such systems to do these kind of new tests of CDM. So I'll just leave you with this, that we have now ways of probing very finely the structure of our galaxy and that of nearby galaxies. You'll hear from Risa and Manoj the wonderful strong lensing observations that probe some subhalos. We've seen in the press that a primordial black hole could be right in our backyard. So microlensing can also tell us about primordial black holes. So these are very interesting areas of study that pursue either dark matter that's a small component of dark matter on top of CDM, or some tweak of CDM. So So I think Andrey is going to pose some of these questions, so I'll just leave you with these and turn it over to Risa.
Okay, I have no idea why this is small on the screen, but maybe it's appropriate to talk about a small structure in the universe. Okay, first I just want to thank the really excellent speakers we had this morning who actually talked about almost everything that I'll cover in this talk. But only about 40% of you were there this morning, so hopefully I'll still be able to say something interesting. I also want to thank members of my group because we had a really lovely discussion about all of these issues earlier this week, and many of them are here, and you should talk to them. So I'll just again start with this question of that Andrey posed to the panel: is a theory beyond CDM needed to explain structure formation? So I'll first just give you my one-word answer. No, at least not at present. Should we, though, still consider alternatives to CDM and test them with measurements of structure formation? I think almost certainly the answer to that question is yes. And I came up with a bunch of other questions. What do we really mean by CDM? It's not obvious people are always meaning exactly the same thing when they say that. What would it really look like to rule out CDM from structure formation? What would we have to convince ourselves of? What predictions of CDM have been verified? How does galaxy formation impact the matter distribution, or the simplest predictions of CDM? And what is the best way to probe dark matter microphysics with structure formation, and what have we actually already learned by doing that? And I think a really important question, which I won't really cover, but I hope we'll discuss in the discussion, is what signatures of dark matter physics are unique. So I'll just start with this very simple question: what do we mean by CDM? So we're talking about a cold, stable thermal particle, and I think the key thing is that there's a lot of ideas for what dark matter might be. Most of them are characterized by some sort of free streaming length, and on smaller scales, density fluctuations are erased or suppressed. So in the context of structure formation, when we say the phrase CDM, we usually mean a model which consists of a particle for which the free streaming length is small enough that it does not impact structure formation, and interactions which are small enough or inconsequential enough that they don't impact structure formation. Now, this is almost certainly an approximation of what's really happening. In most real models of dark matter that are physical, some of these assumptions will be broken in some regime, but they may or may not be broken in a regime that is observationally accessible to us now or even ever in the future. So I think that's an important distinction. Okay, so first thing is, you've already seen this plot. CDM works extremely well over a wide range of scales. This plot is just showing that the power, all the way from the largest we can measure it to quite small scales, is consistent with a very, very simple model with 6 or so parameters. So this model also makes a lot of predictions, some of which we've tested and some of which we haven't tested. For the figures I chose on here are mostly figures from 15 to 20 years ago. When simulations of CDM were very sort of first able to start predicting small-scale structure and also internal structure. Okay, so these are just a few examples. The first thing that CDM predicts is it predicts a clumpy universe with a lot of dark matter halos, and it predicts the number and clustering properties of those halos. it predicts that halos build up hierarchically through a series of small mergers, starting small and getting bigger. And so there should be lots of substructure left over in the current universe, including substructures within substructures, destroyed substructures like streams and stellar halos. It also predicts cuspy profiles in the centers of every single dark matter halo. And it also predicts features in the dark matter clustering. You heard a little bit about that from Boo, of this sort of splashback radius in the dark matter density profile. You also see that in galaxy clustering. You see a feature at sort of the radius of dark matter halos, and that's actually a really, to my mind, one of the most impressive predictions of CDM that's actually been verified in galaxy clustering over a very large range of redshifts. Nevertheless, for some reason, despite all of this success, we've had approximately 20 years of crises of CDM, and actually I was thinking about this. I came to one of the first meetings I came to here in Chicago in 2002. It was all the small scale structure of dark matter. We talked about the missing satellite problem. We talked about the cusp core problem, and this was just, you probably can't read the dates on these citation graphs. These are the number, I just did a full text search for these phrases to see how popular they've become in recent years, but they sort of started in early in the millennium, essentially at exactly the time we were starting to be able to make robust predictions about small scales in these models. And this is just two examples of what's called the missing satellite problem, that you predict a lot of halos and don't find so many galaxies, and what's sometimes called the too big to fail problem, because it happened shortly after the recession, that some of the sort of more massive dwarf satellites don't appear to have baryonic components, at least that we observe. Okay, so in order to address some of these crises, people have come up with lots of different alternatives, and that's really because the particle properties of dark matter can impact the halo population and hence the galaxy population, especially on small scales. And here's just a couple of examples of that. This is from a recent review article by James Bullock and Mike Boyle and Colchin, showing that self-interacting dark matter changes the numbers a little bit and the density profiles a little bit more. Warm dark matter changes the numbers of substructures. And really, many different dark matter models are still viable because these scales are actually not that well tested still to date. So this is just a partial list of some of the ideas people have come up with that are different from CDM. Warm dark matter, fuzzy dark matter, ultralight scalar dark matter, self-interacting dark matter, sterile neutrinos. And many of these models, in some sense, some of them have really robust physical motivations. Some of them were motivated partially, at least when they were proposed, to solve those so-called crises. But many of these models do suppress small-scale power, and some, for example, self-interacting dark matter, also change things in dense regions. Okay. So one concern I have is what some people or at least seem to mean when they say CDM. And what CDM predicts appears to be predictions of n-body simulations with no baryonic matter in it. Okay, so that is CDM, I guess. But I would posit that any viable model of our universe probably does contain baryons, or we wouldn't be discussing it. And it turns out that when you have a universe with baryons, things happen. And this is just a partial list of some of the things that galaxy formation processes do within cold dark matter. Okay, the 15% of the total matter that is baryons has an impact, even though it's subdominant. One of the things it can do is suppress the formation of galaxies, so not all dark matter halos light up. There were many things known about this even from the earliest days of the so-called missing satellites problem. Another thing baryon processes can do is change the profiles of galaxies. So this is an example of these green circles in this paper from Gabernato are the dark matter only prediction. when you add baryons, they often have feedback and they can change the profile, make them shallower. Although not all simulations agree on exactly the extent or the mass range over which this happens, and that's, I think, quite an important caveat. Baryons can change the shape of halos, generally making them rounder, and they can destroy, they can not only suppress the formation of galaxies, they can destroy galaxies that have already formed. This is some recent work that shows, in the Milky Way, just having the Milky Way there, there's a disk there, and many satellites will go through that disk and be tidally disrupted. And so if you ignore that, that can have a big difference, roughly a factor of 2, on the prediction. Okay, so back to this original question, is a theory beyond CDM needed to explain structure formation? I could have answered yes, in the sense that we obviously do need baryons, even in the context of CDM, to explain that. And there's been really an enormous amount of progress on this front in recent years, and this beautiful figure is from a recent review article by Mark Vogelsberger and his talk this morning, showing on the left-hand side simulations of dark matter only, and on the right-hand side simulations of dark matter with baryons. And there really has been a tremendous amount of progress on this front in the last 10 or 15 years. With people actually being able to form galaxies that have morphologies and sizes that look quite a bit like galaxies in our real universe, which was not, that was not true 10 years ago. So I think this is a major achievement of the field. Andrey already showed a version of this plot that Alison Brooks showed this morning in her talk, and I've just made a slightly different version. So what Alison indicated is that in her simulations and other simulation groups that are doing really detailed prescriptions of CDM plus baryons, most of the things that have been labeled problems are actually reasonably well addressed in those simulations. In warm dark matter and self-interacting dark matter, those models have mostly been simulated without baryons, and even without baryons, they solve some of these problems. She also put check marks in her second slide in these boxes, but I think that the jury's really kind of still out on that. There have been actually quite few, they're starting in the last couple of years, but there have been quite few number of simulations that include these alternative dark matter models and also include baryons. So I think it's still a question. And then there were 2 other things that are sometimes listed as problems of CDM that came up in discussion this morning, so I just want to mention them, because I don't think they're totally conclusively been addressed. One is the question of, so in CDM, we have so many mergers going on this whole time. Can you get disks that are as thin as we observe? We do observe in our own universe a wide diversity of galaxy morphologies, but some galaxy disks are extremely thin. And if they have lots of mergers, that's a bit of a puzzle. On the other hand, I don't personally think that any of the simulations have been done with enough resolution that we can even answer this question. And I think, a good example of this is, as I just said, like 10 years ago, we weren't forming things that had the right, even really looked as much like disks, and so there's been a lot of progress there, I think. And then the last thing that's come up quite recently is this question of planes of satellites. The observational situation about this is still a little bit confusing to me, at least, but there have been claims of basically interesting anisotropy in the Milky Way, in Andromeda, and in a large number of external galaxies. I personally still think the jury is still out on this one. Okay, but still, I'll just ask another question. Does it make sense to say there are crises with CDM if we're talking about comparing CDM-only simulations in regimes where baryons are important? I would say the answer is no. But I think there is really interesting dark matter and galaxy formation physics at low mass. The degeneracies are really important, and they're not fully understood. So, many dark matter models do interesting things to suppress power. And the relationship between galaxies and their dark matter halos is very, very uncertain in this regime, let's say from 10 to the 7 solar mass halos to 10 to the 11 solar mass halos. And so I think we want to explore both of these things together. So I do think there are really good reasons to consider many different dark matter models. To my mind, the most compelling reason is we don't know what dark matter is. So we should consider all of the possibilities. There really is little information about it on the smallest scales. So we should look for any possible astrophysics effects that can distinguish between any of the ideas people have that are still viable. To my mind, and maybe it's just semantics, but maybe not, I think it's a less good reason to consider these is that CDM is in crisis. I don't think it is in crisis. Okay, but again, is there information about small-scale structure that can inform dark matter microphysics and galaxy formation? I think the answer is definitely yes. So we should continue to look for this information. So some of the ways we can do that, we can look at how many dwarf galaxies there are, hopefully the smallest ones we can possibly find. We can look at what their profiles are. We can look at strong lensing, which potentially can find not only dwarf galaxies, but even dark matter halos that are below the scale that galaxies can form. We can look for streams that come from disrupted dwarf galaxies or globular clusters, and we can look for subhalos running through those streams to make gaps. We can look for suppression of the power spectrum in the Lyman alpha forest. We can look for the presence of early galaxies, which is sensitive to small-scale structure, and the impact of early galaxies on reionization. There's actually multiple signatures that some of them sort of on the hairy edge right now, and some of them very futuristic that we could potentially look for in 21 centimeter. Okay, so I only have a few more minutes, but I'll spend a few minutes discussing where I think we are with some of these. The one that I worked on most recently is the question of the smallest galaxies that exist, and this has been an extremely exciting field with a large number of discoveries in the last decade. We're now up to approximately 50 to 60 galaxies that are orbiting the Milky Way that have masses, that have stellar masses all the way from a few hundred solar masses to 10 to the 11 solar masses. So it's a huge dynamic range. We heard this morning, and we'll hear a little bit more on Monday about a new search that several of us in the room are involved in, which is exciting because we're really actually looking at most of the sky using DES plus pan-stars. We find about 40 satellites in this system, but I think the exciting thing is not finding them, and we actually did not find any new ones, but is characterizing the selection function robustly and then comparing it robustly to predictions. And the predictions that we're comparing to are CDM predictions, but including a model for the impact of baryons and a very flexible model for how galaxies populate their dark matter halos. And I don't have time to tell you about that, but Ethan Nadler will talk about this on Monday, so you can go to his talk, and if you weren't at Keith Bechtold's talk this morning. But the bottom line is that the satellite counts, so the numbers of galaxies, as a function of luminosity, size, and position on the sky, can be matched with reasonable models for populating dark matter halos in standard CDM. So I think that's a real success of the model. And it's actually somewhat non-trivial. One of the interesting things about this analysis is that we find we cannot fit these data unless we include the presence of an LMC. There not only has to be an LMC, it has to have been accreted within the last 2 gigayears. So, and that's actually in really good agreement with totally independent data from Gaia, which also finds of order 8 satellites that seem to be associated with the LMC. So I think this is a really non-trivial test of hierarchical structure formation, showing that in order to explain this, you have to have satellites of satellites. And these observations do actually constrain dark matter models in interesting ways. And these are just 3 examples of those kinds of the kind of models they can constrain. These models can constrain the interaction between dark matter and baryons, and this plot is from a paper that is published now, which actually shows that dwarf satellites in the Milky Way can constrain dark matter baryon interactions about 1,000 times more strongly than the CMB can. which is pretty cool. They also constrain warm dark matter and fuzzy dark matter models, essentially any model that suppresses the power spectrum. And currently, constraints from Milky Way satellites are roughly comparable to constraints from strong lensing and the Lyman alpha forest. Strong lensing, I think, has a lot of potential in the future. We heard a beautiful talk this morning by Yasha Hezebeh about the detection of substructure with ALMA and the future prospects for this. So with that very high resolution ALMA data, Yasha and we detected this one satellite here, which is perturbing this Einstein ring. So that also puts constraints on the amount of substructure. And I think there's a bright future here. They're actually currently the strongest claim from strong lensing. Recent paper on the archive from Daniel Gilman and Tommaso Treyu and others is that the warm dark matter mass has to be larger than 5.2 keV. But that's still with just a handful of lenses, and this field is about to explode. So those constraints are going to get a lot more interesting in the next decade, and I think there's a lot of potential then there. This is exciting because, of course, this does not depend on having a galaxy in the system. Any dark matter halo could perturb these strong lenses. And as you already heard from Bhuv, this potential that dark substructures, well, either substructures with galaxies or just dark dense substructures, could perturb streams. And there's now a large number of these streams found. A whole bunch more will be found with LSST. And I think this method, actually both of these methods, potentially have the possibility to detect things that are sort of 10 to the 5 to 10 to the 6 solar masses in the next decade, and that's very exciting. Now I just have just 2 more slides. So here's my sort of summary of the status. Annika said this morning that CDM is depressingly robust. I'm not very depressed by it. I think it's quite beautiful and interesting, but it is an approximation in many ways. It's a model that has made several predictions that have seemed to be consistent with our universe. But on some scales, and particularly the scales of sort of intermediate mass dwarf galaxies, sort of just below the classical dwarfs, the predictions depend very strongly on baryon physics. I would claim that modulo this uncertainty, CDM is doing just fine, but that doesn't mean it's correct. It's a class of models that is currently reasonably consistent with the data, and we should continue to probe this and test this. I think there's very little simulation of non-CDM models plus baryons, so I think, and still, in fact, some numerical issues with some of these alternatives that need to be worked out before the predictions are really robust, so I think that's an important area for future work. I think it's quite exciting that we now actually have evidence for substructures that are sort of order 10 to the 8 solar masses from multiple lines of evidence, and that really does rule out many alternatives. Below this scale so far, there's little evidence one way or the other, but upcoming data will test the models on smaller scales. So I'll end there just by saying a few things that I think we should focus on going forward. So the first is the search for the smallest objects we can find, because those are actually quite constraining. If we find those structures, then it rules out a whole class of models that suppresses power on those scales. I think it's possible to get to 10 to the 5 to 10 to the 6 in the next decade. Measuring the internal structures of the tiniest halos that exist is actually quite interesting in terms of distinguishing between CDM and self-interacting dark matter. That's because those things have very few baryons, so they should be less impacted by feedback. I think we have to continue to work hard on the modeling side, both in terms of detailed hydrodynamical simulations to understand the range of possible predictions for a given dark matter model, and with combining CDM simulations with sort of more flexible phenomenological models that can really explore the full range of baryon impact and the connection between galaxies and halos, along with the dark matter degeneracies. So, thanks.
I'll try to give you a slightly different take from what Lisa said. But let me start out by actually agreeing with some of the things she said, which is, when I look at this question, really, in my mind, what I'm thinking is the same thing that Lisa said, which is CDM is an approximation from the particle physics point of view. At some point, we know that it has to break. The question is, where does it break, and is it breaking on scales that are astrophysically accessible? The second question that I think about is, do we have another model that has a simpler and better description of some of the phenomena that we see? For example, the dark matter density profiles in galaxies. And if so, I think that makes it an interesting model to consider and to contrast with CDM. And then the most important thing is, does the other model that you're thinking about have distinct signatures? So I'm going to try and attempt to give you a little bit for both, trying to give you maybe a simpler and better description of some things, and then try to go through distinct signatures. So this is just who said this. Lisa said this. Lambda CDM agrees really well with observed large-scale structure. It's important to keep this at the back of your mind. And so in this sense, CDM is the right description. It's already, in a sense, proven. I mean, I can't imagine what more you have to do to say that something is right. It's gone through huge numbers of tests. Right? But when you think about the particle physics, there are many things you can imagine. So one of the things that I like to think about is that dark sector particles can interact with each other. For most of the particle physicists in the room, this would be normal. You would agree with it. It's not very clear that the astrophysicists would have the same reaction to it. But if you don't, just for motivation, just think about your own sector, visible sector. Everything interacts with everything else, or almost everything, right? You have hydrogen atoms bouncing off of hydrogen atoms, neutrons and protons colliding, and the thing I'm going to tell you now is very similar to what's happening in the visible sector. The nice thing about this particular way of thinking about dark matter, or these models, is that just because of the way we've defined this, right, CDM and SIDM are essentially the same on large scales. Right? They can start deviating, but not on large scales. Because for cosmology, really, what we're saying is you have a Maxwell-Boltzmann distribution or you have a Fermi-Dirac distribution. Cosmology doesn't care. Right? As long as the temperature is low, everything works out exactly the same. So you're not sort of in this regime where a new observation comes in and you got to scamper and move your parameter space somewhere else. That's not going to happen with SIDM. There's just going to be one parameter space, roughly, broadly speaking, and either that's right or that's wrong. So this was first really enunciated by Spergel and Steinhardt. There was a lot of work that came after it. And then sort of my own thoughts are summarized in this paper with Sean Cullen and Haibo Yu. But we really said that, you want to look at cross-sections that are large. So a few bonds per GeV could be 5, 10, at small velocities. But then the cross-section has to fall with velocity. It has to fall pretty reasonably, so that by the time you get to 1,000 kilometers per second, the cross-section can't be much larger than, let's say, 0.1, 0.2, 0.3 centimeters square per gram, right? So of order like 0.1 bonds per GeV. And that is really interesting from the particle physics point of view, because that allows you to actually think about, for example, you can use astrophysics to measure both the mediator mass, with astrophysical observations. And this, by the way, this fall is also sort of what you would see, for example, in the neutron-proton collisions, or for example, if you had dark hydrogen atoms colliding with each other. So it's a very natural, but you can easily write down models that do this. So keep this sort of picture at the back of your mind. This is what I'm talking about for the rest of the talk. Right? So what I'm going to try and, to answer the question, what I'm going to try and do is first use field galaxies as a motivation to show you what part of parameter space SIDM lives in, all right? And then I'll ask the question of what are its signatures and are they distinct from CDM, and we can measure them. So one slide to think about how you need to think about the halos in SIDM. The SIDM halo profile in the region where the stars are is very simple. Again, this is a consequence of the fact that I'm assuming a large interaction cross-section of order few barns per GeV. The cross-section is basically, the profile is essentially isothermal. So the isothermal profile is just e to the minus gravitational potential over kT. This kT, for all practical purposes, and unless the baryons are really important, is Vmax. It's being set by the outer halo, right? And the normalization of the density is being set both by Vmax and Rmax. So it really inherits all of the properties of the outer halo, which come from cosmology, which comes from the power spectrum, lambda CDM. So it's built on the edifice of lambda CDM, and that's why when I show you what it gets right, you will realize why it does so, right? I mean, it inherits all the success of lambda CDM. This simple-looking thing makes a pretty remarkable prediction, which took, seems simple now when I look back at it, but it took me some time to actually realize. And what it says is that in high surface brightness galaxies, the dark matter is going to be cuspy. So if you've heard that SIDM predicts cold halos, that is just plain wrong, right? In high surface brightness galaxies, dark matter density profile is cuspy, and that's because the phi here is the gravitational potential of dark matter and baryons. If the baryons sink in and create a high surface brightness galaxy, so a compact galaxy, the contribution of the baryons is high, and you will actually get something that's dense. For example, in the Milky Way, an SIDM solution essentially looks the same as the CDM solution all the way on until you hit something like a few hundred parsecs. Right? If you didn't take these baryons into account, you would have a core in the Milky Way that's like 20 kpc, right? Completely different. The baryons do matter here. And in low surface brightness galaxies where the baryons are not important, you will get large cores, right? So right off the bat, this is a key prediction of SIDM. How does it do? So here is a compilation from a paper that was in PhysRevX, where we've tried to make 4 panels. These 4 panels are distinguished by the fact that each one asymptotes to roughly similar velocities. So here, these are galaxies. So this is a circular velocity versus radius, where it's asymptoting to about 80. Here is about 120, 150, and this is in Milky Way, L star, and bigger galaxies, right? The color coding is sort of, is telling you something about the surface density. So if you see like blues and greens, they're high surface density. If you start seeing yellows and reds, they're low surface density. And even from the back, you can sort of get a sense that as you get bluer and greener, the curves start rising up faster, right? And this is what is called the diversity problem, which is that at a fixed flat part of the rotation, there's a whole range of densities in the inner part. And what I want you to get out of this is that that is not just random scatter. It is correlated with the stars. It's correlated with the surface density of stars. Okay? So when the surface density of stars is high, you don't see any need for cores in galaxies. When the surface density of galaxies is low, you do see need for cores. That is why I work on SIDM. Because right off the bat, that is a prediction of SIDM. It's a prediction of the fact that the inner part of halos is thermalized. Right? It gets that right. You don't have to, you don't have to vary parameters. You don't have to do anything. Right? So let me contrast this with, the huge amount of progress that's happened in terms of feedback. This is a tricky plot to explain, but let me try to go through it. This is a plot of the circular velocity versus radius. In the background, I hope people can see from the back, there's gray curves. These are taken from the Nihao simulations. The points are just data. It's just a set of data to give you the full sort of range of rotation curves here. And so as many speakers, and as Alison told us in the earlier today, that simulations have been remarkably successful at producing cold halos. And that, I claim, is the failing, which is that what you do to dark matter, perhaps you do to stars. So when you do drive the dark matter out, in the simulations you see that you also drive the stars out. So you're very good at making low surface brightness galaxies, not as good at making high surface brightness galaxies. This is really not a case of like trying to look at the rotation curves and see if it rises fast or not even. These guys rise fast because there's a lot of stars in the center. So my message here with this plot is that getting the scatter, getting both the high surface brightness and the low surface brightness is important. That is the test, that is a key test of your feedback mechanism. And if I look at this, and maybe I'm a little naive, but my take on this is that the current feedback models have to be changed. And if they have to be changed, all of the ticks that you saw on those plots have to be changed.
Could you show where I can see that this has to change?
So these simulations
Yes.
are very good at producing big cores, but there's none of them that looks like this, right? And the reason that none of these gray lines look like that is because,
I don't know if everyone can see,
There's a
but
gray line.
the gray lines span here.
What are the model curves?
Oh,
Those are the model curves.
Those are the
those
so
faint.
those sorry.
Curves that go through the data points.
Those are SIDM fits.
Thank you.
Sorry, those are SIDM fits. Yeah,
That's very confusing.
forget about the solid lines. Just look at the data. Yeah. Well, don't forget about it. That's SIDM. But all right. So why does SIDM get the rotation curves right? And I've already told you this. This is a plot of the inner profile. So the slope of the inner density profile versus the stellar surface density, and these are all the spark galaxies, right? And so these are cores, what you would define as cores, and these are what you would define as cusps. And you can clearly see there's a lot of scatter, as you would expect in any structure formation model. We can clearly see this correlation, that you get cores in SIDM only when the surface density is low, and then when the surface density gets high, you just get this scatter, but they're all almost always cuspy, right? Whereas the current generation of simulations, what they're predicting is, and just look at the pink band here, they predict a correlation with the stellar mass essentially. So there's some stellar mass to halo mass at which you get the maximum core-like behavior, and then you see this fall off, right? So one way to maybe test this is to go this direction. And that's what Risa was talking about, is getting to like small galaxies where the differences between SIDM and CDM are much more apparent. Right? So I could stop here and you can ask me, why am I telling you that CDM and CDM defined correctly, CDM plus baryons is ruled out. And you can't say that for the simple reason that I've already told you that I don't believe the feedback model is right. So when the right feedback model comes along, I'm not sure what's going to happen, right? Maybe it'll fit, maybe it won't, right? The message I'm giving you is that this model, SIDM, is essentially going to give you the right diversity. It's going to give you the right rotation curves, right? So it is a success there. So how do we test this? I think the way to test this is really going to the smaller galaxies. So I've been talking about field galaxies, but the exciting thing, and we heard in the morning, we heard from Risa and Wolf that the exciting thing is really getting to the smaller scales to look at the satellite galaxies. I will flash this picture up. This is from the seminal work by Mark Fogelsberger, Zavala, and Lowe, where they simulated the subhalos of a Milky Way halo. It's very interesting to me always to look at this. And I know why they said this. So this is a model with a cross-section of 10 centimeters square per gram, and they're saying it's ruled out. And it's ruled out because if this was 10 centimeters square per gram all the way for all velocities, you would be in trouble. But on small scales, for small velocities like 30, 50 kilometers per second, then it's fine. There's nothing telling you, there's nothing ruling it out, right? In fact, this is actually, in my mind at least, the best solution to too big to fail. It has the right scatter, it does everything correctly. You can also see something interesting already in this simulation, right? Which is this guy. It's really dense. And I'll tell you in the next slide why that is. And that's the key, that's going to be the key thing to testing it. All right, let me come back to that in just a second. So one more plot about the physics of SIDM, and this is like sort of a key plot if you get, to keep at the back of your mind. What's plotted here is time, so age of the universe over some interaction time. And on the y-axis is the core density, so the density of the core of the halo in sort of with this rho s, which is this NFW density scale. And you see what you expect as time goes on, the core gets lower and shallower and shallower, and then it sort of hits this minimum, which is around 2 to 3 times rho s. And then the generic behavior at this point is that so all along this curve here, you've been mostly transferring energy from sort of the middle part of the halo inside, when you get here, you become mostly isothermal in the inner part, and you start transferring energy outwards, and that sets in a core collapse phase. Okay, so every SIDM halo is going to go through this core collapse phase. Now on the top, I have this cross section listed. And so at the present time, if you need a halo in the field to core collapse, you will need to be somewhere around 30 or 40 centimeters square per gram. But if you're a subhalo and you lost mass from the outer part, you've lost that heat band in the outer parts, this process gets accelerated. And even within, even if you're at a 5 or 6 or 10 centimeters square per gram, you can actually core collapse. And actually this depends very sensitively on what the concentration of the halo is. Okay? So this is a signature that's unique to SIDM. When you core collapse, you get these dense 1 over R squared profiles, which are very different from the NFW 1 over R profiles. And I'm hoping that down the road, this is the way to actually test these things. Okay. So this is just an explicit example of that. Here is a low concentration halo that got, here's a low concentration halo that fell into the Milky Way. It started out like that. If you jack up the cross section, so this is 3 centimeters square per gram, 10, this low concentration halo will just start getting lower and lower concentration. Right? It just gets very diffuse. Many of them won't survive. If they survive, they'll get diffused. This might be the crater tool-like objects, which are very diffuse on the sky. And as a contrast, here is something with a high concentration that fell in. The self-interaction time scale is shorter here, and you can see what's happened. Even with 3 centimeters square per gram, it's denser than CDM. For 10, it's a core collapse. Okay, this part here is almost 1 over R squared. This is just part of the SIDM phase space. I mean, it's not something you tweak. It's built into it. Either this, and this is key. If this process was not there, I'm pretty sure that the Milky Way satellites would have ruled SIDM out, like without this process. Just the same way as if that process I showed you when the baryons are important in setting the SIDM density profile, if that wasn't there, SIDM is not a viable model. Right? So it's really key that you're discovering this physics that's part of this parameter space that's actually required for things to be right. Right, and so I won't say, Lisa already mentioned this, so let me skip it, but the ultra-faint satellites are really a great test bed, and LSST will be amazing for this, and Keith told us a bit about it in the morning. Right, so I have 2 slides on dark subhalos. So we've been talking about visible satellites, but Reese also mentioned dark subhalos, right? So let me flash 2 things. One is again from the same group that Risa mentioned, Daniel Gilman, Xiaolong Du, and ThomasAtre and company, where they looked at 10 or 11 systems. They're looking at flux ratio anomalies, so these are not direct imaging. These are not astrometric perturbations. They have detections, so this is just sort of Dalal and Kochanek, but with more now data set. And they can try and put a constraint on the concentration mass relation using these 11 halos. Okay, these are the CDM predictions. This is sort of their median value. It's not clear to me this method is incisive enough, but all I want to say is if it really was, this is a plain image. SIDM and CDM are different, and that was shown by Mark Vogelsberger's work, but also Annika Peter and a student Dooley and Mark and company. On average, SIDM subhalos are less dense than CDM, right? If there was a way to shrink this error bar, you would be able to see this, right? I mean, but the median here is much more consistent with SIDM than it is with CDM. Right? The other way you can do this is to actually just see the subhalos with their astrometric perturbations. Right? So that's this plot here. I guess people at the back can't see this, but you've heard enough about this. So this is Simona's detection in 2009. This is a different one, which is the looking at the streams and seeing if something has gone through the stream, right? And this is Anna Bonaka's work, where she and her collaborators claim that you need something like 10 to the 8, 10 to the 7 solar mass object, but very dense. I claim that both of these guys are really dense objects, right? And they're more consistent, in my view, with something that's core collapsed than with CDM subhalos. So my message here is not I haven't done enough work here to tell you conclusively. My message is that these kinds of tests are actually sensitive to the density profile of the subhalos. And I think this is really the way to tell apart whether it's SIDM or CDM, because in both cases you will have these dark subhalos floating around, but their density profiles will be different. And the reason in SIDM is going to be different is because the only way in SIDM something is going to survive very close to the center is if it had core collapse. Right? So to me, maybe the question to answer is this. I'm not trying to be facetious, but every single time you work on something like a new dark matter model, you got to ask yourself, right? Am I doing everything to explain the data I see? And then you can ask yourself, do you need something else, or you need another model to go beyond it? I think, as it stands now, SIDM is really an excellent explanation for all of the astrophysical data we see, and I'm looking forward to finding ways to break this.
Could you define SIDM regarding the cross sections?
All right. So first, I'm done with the talk, but then I'll.
CIM is SIDM.
So
what is SIDM? When
at low velocities, you want something like 10 pounds per GeV. So cross section over mass should be something like that. Now, what does it? I don't know. But it has to, again, it has to be velocity dependent. So, for example, if I'm thinking of an elementary fermion, then the mediator has to be lighter than the dark matter. So the mediator mass over the dark matter might be something like 10 to the minus 3. So MEV dark matter, GeV, MEV mediator, GeV dark matter. But that's just one example. It could be a dark hydrogen atom. That works fine. In that case, the scales are 10 to 20 GeV. Okay.
This is just to bring up some of the points that were made by panelists. Sort of the most salient point to get the discussion started. But I'm going to invite first Wolf, Risa, and Manoj to maybe make some comments, some additional comments to these points that they already mentioned during their talks. Comment on.
All right. So as I mentioned, I think it's very fun to think about other components in the dark sector that we're that don't necessarily make up all of the dark matter. And so primordial black holes have a few windows in mass range that are very intriguing. And there could be, there was this proposal a few years ago that to aid the formation of supermassive black holes, how do you get a 10 to the 9 solar mass black hole at a redshift of 6? They said you'd need less than 1% of dark matter to be dissipative, and then it could form the proto black hole that would grow quickly enough. So that particular model, I think, is disfavored, but it illustrates the idea that we have some number of puzzles in astronomy, and it's not too crazy to come up with a subdominant component that addresses a puzzle that stands some test of time. So that's what I have.
So why should it be subdominant and not a whole dark matter in primordial black holes? Is that to...
primordial black holes as the main component of dark matter are ruled out by microlensing.
That's not true.
And other constraints.
Based
Sorry?
on mass, and based on the distribution.
Yeah, light matter.
If you have monochromatic, just one mass, you're right. 100% of the halos will not be in those masses, but if you have a wide distribution, and it's actually clustered, then that's easy. It's perfectly consistent.
So technically, primordial black holes would be still called dark matter, right? They just yeah. So just so it's still within the realm of CDM. It's just not wimpy, not WIMP CDM.
Not a particle. It's a big particle.
Particle. That's some yeah.
But these are compact
Fair
objects.
point.
I have a question to Booth. So one thing that Booth mentioned, which I was very intrigued by, and I'm still waiting for a paper, but the result is very beautiful, which is a constraint on self-interaction of dark matter using the warps in thin disks in clustered environments. And given the strong arguments that Manoj presented for self-interacting dark matter, how would you guys reconcile? So I would ask your opinion because you couldn't find any signatures of self-interaction based on warps, and maybe Manoj to comment what is your view of that particular constraint, the prospects and the current status, whether you think it's a problem for SIDM. If we have to now discuss the challenges to SIDM and not to CDM, do you think it's a challenge?
Okay, let me just explain the physical picture. So if you have a disk galaxy that's falling into a group or a cluster, then there's the stellar disk and the dark matter halo, which is still dominating on large enough scales. So the subhalo of the disk galaxy will get slowed down due to self-interactions, and it'll pull, sorry?
Hydrodynamic threat. There isn't a hydrodynamic system.
Let me finish the thought and then we can discuss it. So the dark matter, the interactions between the dark matter of the subhalo and the parent halo will cause it to slow down, and it'll pull back on the disk, which produces a characteristic warp in the direction that it's falling. So generically, a disk galaxy in a cluster environment would be would warp and then maybe oscillate as it responds to the gravitational tug. Observationally, it's a challenging test to carry out because you can never be sure if a particular galaxy is in the cluster or not. Like, in the transverse direction, you know where it is, but in the line of sight, it's hard. So it's easy to carry out the test in the following sense that you can do a census of how many disks with this particular kind of warp you see. And we haven't done a rigorous census, but you see very, very few such disks.
So just to say, but that's what you would expect, because in clusters, at the velocities at which the subhalos are falling in, I don't expect a cross-section much bigger than 0.1, or 0.2, right? So it's very hard to, yeah, because
in clusters, the cross-section is, so everything you said essentially was assuming the velocity-dependent cross-section which falls towards clusters.
Without that, I don't think it works.
Okay, yeah.
I think you need a velocity-dependence.
So a cross-section that's 0.1 or smaller would evade this test in clusters, yeah. But point few is testable.
That'll be great if you can. Maybe you can test it in groups or some other place where the cross-section could be a little higher.
Right.
So these are exactly the kind of stuff. Because on clusters, there are constraints, and then the constraints that we have are sort of more on galaxy scales. There's this dearth of constraints on the group scale, or like Slack's lenses kind of thing, like bigger things.
But I don't think that a halo falling at high speed into a bigger halo is slowed down by dynamical friction by this effect. Because what happens is the interactions are happening at an individual particle level. So because the infall velocity is large compared to velocity dispersion inside the halo, there's a halo from the big object, particle from the big object will hit a random particle in the small object. Both will immediately leave the system, and the other particles keep moving at the same velocity. So there is no change there's no momentum transfer to the part of the halo that continues.
Yeah.
It just loses some mass.
Yeah, unless
You
you
make a good point that you do need the scattering cross-section to also be anisotropic.
What?
to debate the point you mentioned that
So you have small momentum transfer, and then you're going to drive.
If you have small momentum transfer, that's true. But
yeah. Yes, so this doesn't apply to generic SIDM models, but if, just as you expect generically a velocity dependence, you may also get an angle-dependent scattering in which you have it.
There's a question at the back.
Yep.
So most of the primordial,
I see, good catch.
so most of the primordial black hole constraints so far, they have they're monochromatic, and to what scale could we set up a spectrum of primordial black holes? And when we allow a spectrum exist, what's the fraction of the constraint of this guy?
Come to my talk on Monday.
Thanks.
What if she's not here on Monday?
Are you here?
I'm leaving.
Say a couple of words.
Just one thing, since there's this talk of the primordial black holes, one other interesting thing for people who want to work on this is that since the early days from 2000, when SID was first proposed, it was understood that when you core collapse, the most likely end state is that a small fraction of your core is going to just become a black hole. Because there's, generically, and that's true even if you allow some new particle physics where you have some cooling processes to happen, you will core collapse. Now exactly what fraction of the core mass actually turns into a black hole, it's hard to know. I mean, with Kim body, we try to estimate this. It's anywhere. There's an order of a few orders of magnitude. It could be 10 solar masses. It could be 1,000 solar masses. But I think at some level it has to happen. And so this is something that nobody's actually really worked out or thought about. But a lot of the small subhalos in SIDM should have small black holes sitting there. I don't know what the spectrum is, but they should exist in these theories because that's the generic end state of core collapse.
So with regard to dissipative dark matter, I think the problem with dissipation is, as you probably know, that if the fraction of dark matter that's dissipative is large, then it would settle into a disk, and disks are unstable, self-rotating disks are unstable. So the same reasoning that people invoked early on, the people's on a striker, that dark matter has to be spherically extended, sort of argues against significant fraction of dark matter in dissipative component, but a small fraction comparable to baryon fraction is possible. It's not too bad.
Yeah, I mentioned this just because there's a particular example, but the generic physics is just of dark matter interactions with standard models or with a subdominant dominant.
And with regard to your second question, so Risa, maybe you can comment. My impression from the strong lensing projections and from the expectations for the gaps and spurs in the stellar streams is that it's roughly 10 to the 6, 10 to the 7 solar masses. I don't know if we can expect from any observations to go to probe lower substructure, but it seems like 10 to the 6, a few 10 to the 6 is reachable.
I think 10 to the 6 is reachable. There's some claims of 10 to the 5. I think there's a lot of theory work that needs to be done, both for strong lensing and for the streams before that will be robust. But it's possible. But I don't think we are going to get a lot smaller than that.
So why do you need the theory for strong lensing? I understand why you would for the streams, but the lensing geometry is.
Oh no, the lensing.
It's how to find
the lensing geometry is straightforward. But it's quite sensitive to environment, to the profiles of the substructures themselves. I think that's just not where it needs to be for those. I mean, none of the constraints right now have fully explored. Manoj was emphasizing this too. Have fully explored the range of profiles for the substructures.
I understand, but the theoretical, the strong lensing effects for distant lenses are dominated by field halos,
Sure.
5 subhalos.
Yep.
And there the structures are actually relatively easy to calculate in a particular dark matter model. So,
Yeah.
so I think that part is there. Getting an observational setup which you can really be sensitive to such small masses, that's pretty hard.
Yeah, yeah. And there's a lot of analysis work to be done on the data. I actually wanted to ask a question about Manoj's final point. Maybe not to Manoj, but to other people. So Manoj explained very nicely how self-interacting dark matter can get that diversity of rotation curves. And I actually agree that, you know, almost certainly we're not done with feedback models, and there's a lot of work to be done there. A question for people who you know, are actively working on those models, they're almost certainly too simplistic now, but is there a plausible way that you can get this diversity with, you know, with reasonable feedback over this range? So maybe people who work on this.
Yeah, so I think, you know, there is diversity already even in the standard model from variations in concentration and history. There's another part of the diversity which hasn't been fully looked at, which is this in translating from small galaxies, which are typically irregular, directly to the observables, which is some two-dimensional velocity field. There's actually a lot of scatter that comes in just because the objects are not regular. And so this part of the diversity is there too. So it's important to actually, this is the point we were making in a different context this morning, you really have to mock up properly the observational process, because that introduces scatter. And you can't just compare things at the level of an apparent rotation velocity. That's not good enough. So I think it's clear this introduces more diversity. It's controversial whether it'll produce enough.
I think there's another response back there.
Is it going to
So I had a question about the attempt to suppress power on small scales, invoking warm dark matter, whatever. That's going to create a tension with early structure formation. You're going to reducing power will make it difficult. It's been called the catch-22 problem by Andrey Kravtsov, I think. Could you comment on that? Is that an issue that one should worry about still?
I think it is, although my current understanding of the situation is that you know, we already need to have structures sort of 10 to the 8, 10 to the 9 in the local universe to explain, you know, strong lensing and the dwarf galaxies in the Milky Way. So I think that once you have those structures, you're actually, at the moment, pretty okay at high redshift. The situation might change, you know, with JWST when we see what's going on at redshift 15, and we'll see what we find. But I think that the strongest constraints right now are in the local universe, not the early universe. But we do have to do them both simultaneously. I think that's important.
Sure. Well, we are observing very quiescent galaxies of very high redshift, which must have fallen much earlier.
Absolutely.
So there's definitely an issue of where those seed fluctuations came from.
Absolutely.
Yeah, so going back to the, I guess I'll just stand here. The last point, right, so the discrepancy that you showed between the rotation curves in Nihao and those that have been observed are large, but at the same time, Nihao simulations are only zoom-in simulations. So could you, I mean, is there any possibility that we just have not explored the parameter space of dark matter halo accretion history that could give rise to these concentrated stellar profiles?
It's totally possible. Like, you know, I've spent time looking at the Nihao guys. I've talked to them. It's not very clear that they've selected the galaxies in any specific way to lead to low surface brightness galaxies.
Yeah.
So, you know, all I'm saying is, like, you know, roughly half the galaxies have smaller sizes, have Morphe. You want to get them both right.
Yeah.
I agree it's a hard problem. You know, they had to do this because that was computationally the only thing. Where other people, I don't know if Alison is still around, maybe she can comment. Other people are doing like bigger boxes that may be less unbiased.
Alison, I think she may have left already, but her legacy lives on. So I wanted to bring this up. I don't know, maybe Malshi, you can comment. Alison is not here to defend, but she was very convincing this morning that baryonic physics in all of the modifications of CDM solves, well, actually solves all the problems except for the diversity, I guess. Yeah. Diversity had question marks, and it's only, so I guess she's agreeing with you that SIDM was...
What I said is also that, if you don't, if the problem is in your implementation, right? So just for a moment, believe me that there, the feedback model isn't set in stone, right? That there is a problem.
I think we're happy to believe that.
All right, so if you're happy to believe that, then it affects everything else because, okay, this core cusp problem isn't really a separate problem. It's just part of the diversity, right? I don't know, she separated it out. I guess it's just a question of do you form a core or not. But it's really the same thing, right? Too big to fail, missing dwarfs. I mean, maybe you don't want to call it too big to fail, but I like it because that, I don't know the paper, but they're all related, right? So there's really two problems here, right? And then the bulgeless disk galaxies. Okay, so three sort of problems.
Thin bulgeless disk galaxies.
Thin bulgeless disk galaxies. So if you don't get the feedback right there, it percolates through everything, right? So it's not a matter of just ticking one box because her whole point is it's all a correlated ecosystem.
But Manoj, as somebody who's a little bit far from this field, I do have like this annoying sociological worry about it, that does one just continue improving one's feedback model until the simulation of that particular model agrees with the data?
Some people would say yes, that's
yeah, I mean, I would argue that right now, those models are data-driven.
But does that not make that whole genre of tests not powerful tests?
I think it shows that the biologic physics could solve the problem. I don't think it shows that it does solve the problem. So for example, you need a certain kind of very bursty feedback which causes oscillations in the gravitational potential. That is testable because you can go and observe star-forming regions in real galaxies and see if they are compact enough and rapidly evolving enough that they could cause such potential fluctuations. So I think you need to go and you find out what kind of feedback model could solve the problem. Then you go look at real galaxies and see if that corresponds to what they're doing.
So Andrey, I have a question for you actually, related to this. So this is the same thing. So I've seen some papers where they're talking about correlation of gas density on small scales, right, and star formation. So there's the usual Kennicut law where we know that the gas density is correlated with star formation rate. But there's some indirect now evidence that if you look on scales that are smaller than 100 parsec, right, observationally, this correlation goes away. So there's a lot of scatter.
Yes.
And one of the things that's true in the simulations is that this correlation, is very strong, right? So.
Well, depends.
Well, I mean, at least in these strong feedback models that when I call strong, that's true, right? It's a supernova, star formation happens, supernova happen, and they drive all the gas out.
Well, that's a complicated issue. I can talk to you afterwards.
But I mean, that might be another observational handle, right? I mean, it's trying to get down to these small scales.
I think without going into detail, your point about the need to really pay attention to the feedback models in the context of this, and also in the context of explaining particular correlations that data show, particularly with diversity, that that you have to explain not just diversity with feedback. And I saw that people did claim that diversity can be solved by feedback, but the fact that it's a correlation with surface density that has to be also respected, that the data shows. And the fact that only certain types of feedback can do this. It's not just any baryonic physics or any feedback, it's a particular bursty type of feedback. But feedback of particular strengths, this is a very good point. I think we know from modeling galaxy formation that feedback is needed to solve all the issues that models of galaxy formation faced for decades. And at the same time, this context actually provides a very useful additional constraint and additional sort of testing ground for the models of feedback. But I also think that this scorecard actually demonstrates that you cannot really answer this question or move beyond it without simultaneously developing both alternatives to CDM and improving models of galaxy formation, the baryonic physics.
So I wanted to call out a different type of model, just because of this idea that Lam Hui showed that with the wave-like nature of ultralight, axion, fuzzy dark matter type models, you can explore new phenomena, and they're just starting to find these vortex structures that propagate and disappear, and they could show signatures in, Gaia-type observations of Milky Way stars. So there may be fun new directions that one can pursue with, models other than SID.
Yeah, this morning, one of the surprising things in the morning session was that there's a lot of excitement and new result and new work studies on the fuzzy dark matter, ultralight scale dark matter, which is not a new idea, but only recently simulation started to sort of explore this in a linear regime. And we cannot cover this in the panel discussion, but there was a lively discussion and interaction about this in the morning session. Any other final thoughts or comments?
If I got this right. So, tell me if it's fair to say this, that the self-interacting dark matter was really introduced to solve the core problem. I mean, you had the self-interaction and would solve the core problem in CDM, but now you're saying the opposite. That the main smoking-gun signature of the self-interacting model is the core collapse, is the formation of the singularity. Is that right?
That's true. Yeah. It's funny the way it goes.
Okay, yeah, I thought, I just want to make sure I had that right. Yeah.
Okay, so I think it's time to break and continue the discussions during the reception, but before we break, Rocky will make an announcement.
Okay, we will see everyone here tomorrow morning at 8 a.m. for the continental breakfast, and starting at 8:30 in this room, we will have, at 8:30 we will have the session on cosmic acceleration here in this room.
There's an incorrect schedule on the people's show. Some people think it's not. It's at 8:30.
It's at 8:30.
Yeah.
And 8:30 in room 100 will be the session on inflation. And Andrey, you should thank your panelists and break for the posters.
Yeah, let's thank the panelists and all the speakers.